This is the fourth video for mathematical induction for extension 2, and we're looking at induction with trigonometry. We're going to look at the 2009 HSC question 8a, and there are 4 parts to it. So we're just going to start here with part A, using the substitution t equals tan theta on 2, or otherwise show this result that cot theta plus a half tan theta on 2 equals a half cot theta on 2. Now, using the t results, if t equals tan theta on 2, then we know that tan theta is equal to 2t over 1 minus t squared. So therefore cot theta will equal 1 minus t squared over 2t. So therefore cot of theta plus a half tan theta on 2 is equal to 1 minus t squared over 2t plus a half times tan theta on 2 is t. So that, if we make a common denominator, that's 1 minus t squared over 2t plus, at the moment we've got t over 2, so multiplying numerator and denominator by t, we've got t squared over 2t, which is 1 minus t squared plus t squared, which is just 1 over 2t, which is 1 half times 1 over t, which is 1 half times 1 over tan theta on 2, which is 1 half times cot theta on 2. Part of the question is done. Now part 2, use mathematical induction to prove that for integers n greater than or equal to 1, that the sum from r is 1 to n of 1 over 2 to the power of r minus 1 times tan x over 2 to the power of r equals 1 over 2 to the power of n minus 1 times cot of x over 2 to the power of n minus cot of x. Okay, let's start with step 1. Prove true for n equals 1. So on the left hand side we have 1 over 2 to the 1 minus 1 times tan of x over 2 to the power of 1. That's 1 over 2 to the power of 0, which is 1 over 1, times tan of x on 2, which is equal to tan of x on 2. Now the right hand side is 1 over 2 to the power of 1 minus 1 times cot of x over 2 to the power of 1 minus 2 times cot x. Now 1 over 2 to the power of 0 is 1, so we've got cot of x over 2 minus 2 cot x. Now we know that a half times cot theta on 2 is cot theta plus a half tan theta on 2, so therefore cot theta on 2 will be 2 times this left hand side. So therefore cot x on 2 is 2 times cot x plus a half tan x on 2. So that's our substitution for cot x on 2. We've still got minus 2 cot x there. Okay, now expanding, we've got 2 cot x plus 2 times a half is 1. So we've got tan x on 2 minus 2 cot x, and that is equal to tan of x on 2. So therefore it is true for n equals 1. Now we assume true for n equals k. That is, we are assuming that the sum from r is 1 to k is equal to 1 over 2 to the r minus 1 times tan of x over 2 to the power of r equals 1 over 2 to the power of k minus 1 cot of x over 2 to the power of k minus 2 cot x. So that's our assumption. And step 3 is to prove true for n equals k plus 1. That is, we want to prove that the sum from r is 1 to k plus 1 of 1 over 2 to the power of r minus 1 times tan of x over 2 to the r is equal to 1 over, now we've got 2 to the power of k plus 1 minus 1, which is 2 to the power of k, times cot of x over 2 to the power of k plus 1 minus 2 cot x. Left hand side is equal to the sum from r is 1 to k plus 1 of 1 over 2 to the power of r minus 1 times tan of x over 2 to the power of r. To the sum from r to 1 to k of 1 over 2 to the power of r minus 1 times tan of x over 2 to the r plus the last term. So if we're going from r is 1 to k plus 1, here we're going to go from r is 1 to k because we can substitute in here this assumption, plus we need our last term, the k plus 1th term, will be 1 over, remember we're going from r is 1 to k plus 1, we go k plus 1 minus 1, which is 1 over 2 to the k, times tan of x over 2 to the power of, we're going from r is 1 to k plus 1, so the k plus 1 term will be tan of x over 2 to the k plus 1. Now, using the assumption, we know that this bit here is equal to 1 over 2 to the power of k. Sorry, we're using the assumption here that this bit is 1 over 2 to the power of k minus 1 times the cot of x over 2 to the power of k minus 2 cot x, and we've still got plus 1 over 2 to the power of k times tan of x over 2 to the power of k plus 1. This is using the assumption. Over 2 to the power of k minus 1 times the cot of x over 2 to the power of k minus 2 cot x plus 1 over 2 to the power of k times tan. Now I'm going to write this, break up this index, x over 2 to the power of k times 2, or times a half, I suppose. Okay, so times a half. Well, I'll just fix that up. Half, because 2 to the k plus 1 is 2 to the k times 2 to the power of 1. Okay, now that is equal to, that's equal to 1 over 2 to the power of k plus 1. Now we're just going to do a substitution here because we want to use our result from part 1, which is cot theta plus a half tan theta on 2 is a half cot theta on 2. Because if we look down here, we've got, if we let theta equal x over 2 to the power of k, so let theta equal x over 2 to the power of k, this will become 1 over 2 to the power of k minus 1 times cot theta minus 2 cot x plus 1 over 2 to the power of k times tan. Now this bit's theta, theta times a half is theta on 2. Now if we look at our result from part 1, what I'm going to do here is factorize out 1 over 2 to the k minus 1 with these two terms, and I've got cot theta plus 1 over 2. So to get 1 over 2 to the k, I've got 2 to the k minus 1 plus 1 will give me 1 over 2 to the k there. So tan theta on 2. Now if we go back to part 1, cot theta plus a half tan theta on 2 is a half cot theta on 2. So making that substitution, so I've done that plus that, and we still need here the minus 2 cot x. So making this substitution from part 1, we've got 1 over 2 to the power of k minus 1 times a half cot theta on 2 minus 2 cot x, which is equal to 1 over 2 to the power of k minus 1 plus 1 is 2 to the power of k times cot of theta on 2, can't see that, minus 2 cot x, and we know that theta equals x over 2 to the power of k, so we're just about there. So that's 1 over 2 to the power of k times cot of x over 2 to the power of k times 2 down there, because it's cot theta on 2, minus 2 cot x, which is our desired result, 1 over 2 to the power of k, cot of x over 2 to the power of k plus 1, minus 2 cot x, which equals the right-hand side. So therefore, this is proven true for n greater than or equal to 1 by mathematical induction. Okay, that's the end of that part 2. If the questions show that the limit as n approaches infinity for the sum of r is 1 to n of 1 over 2 to the power of r minus 1 times tan of x over 2r equals 2 over x minus 2 cot x. Okay, let's start with from part 2 with our, sorry, I'll just bring that back up, with our mathematical induction. Notice we're starting with the same thing. We know from part 2, so from part 2, we know that the sum from r to 1 of n of 1 over 2 to the power of r minus 1 times tan of x over 2r is equal to 1 over 2 to the power of n minus 1 times cot of x over 2 to the power of n minus 2 cot x. Now that's from our proof, our induction proof in part 2. Now if we let theta equal x over 2 to the power of n here, then, sorry about that, if we let theta equal x on 2n, so that will be theta, we just want to write this here in terms of theta as well, then I can put that theta over x is 1 over 2 to the power of n. Notice we've got 1 over 2 to the power of n minus 1. So, therefore, both sides by 2, therefore 2 theta over x equals 2 over 2 to the n. So therefore 2 theta over x is 1 over 2 to the power of n minus 1. So therefore 1 over, so just working with this right hand side, continuing from here, 1 over 2 to the power of n minus 1 times the cot of x over 2n minus 2 cot x is equal to 2 theta over x times cot of theta minus 2 cot x, which is 2 over x times theta over tan theta, because cot is 1 over tan theta, minus 2 cot x. We're looking at the limit as n approaches infinity of this. To look at the limit as n approaches infinity, now we have this relationship here. So, as n approaches infinity, then x over 2n will approach 0. So therefore, we know that theta is x over 2n, so therefore theta will approach 0. Now, if theta is approaching 0, we know that the limit as theta approaches 0 of theta over tan theta is equal to 1 from that extension 1 result. I'll just put since. So since the limit as theta approaches 0 of theta over tan theta equals 1, therefore, as n approaches infinity, 2 over x times theta over tan theta minus 2 cot x will approach, we know that this is approaching 1, will approach 2 over x minus 2 cot x as theta over tan theta approaches 1. Our desired result, that the limit as n approaches infinity is 2 over x minus 2 cot x. And so therefore, we can just write our conclusion. Therefore the limit as n approaches infinity, sum from r is 1 to n over 1 over 2 to the power of r minus 1 times tan of x over 2 to the power of r is equal to 2 over x minus 2 cot x. And now for part 4 of the question, hence find the exact value of tan pi 4 plus a half tan pi 8 plus a quarter tan pi 16, etc. From part 3, and looking at this from part 4, we can see that if, remember we're starting from r is 1, so if r is 1 we get 1 here, 1 over 1, tan of x over 2, but we want tan of pi 4. If we look at r is 2, we get 1 over 2 to the power of 2 minus 1 is 1, so it'll be a half tan of x over 4. Now we have x over 4. If we let x equal pi on 2 for both of these, and also for the third one, then this will start to look like this series here. So if we let x equal pi on 2, then we've got 1 over, so starting with r is 1 over 2 to the power of 0 times tan of pi on 2. Remember, we're letting, this is for r is 1. Remember, we've got tan of x is pi on 2, but we've also got times 2 to the 1 here, or times a half, okay? Plus 1 over, now if r is 2, we get 1 over 2 to the power of 1, which is a half, tan x, x again is pi on 2 times, we've got down here 2 squared, plus, again, if r is 3, here we've got 1 over 2 squared, which is a quarter, tan pi on 2 times, here we've got, so x is pi on 2, and we've got 2 to the power of 3 here, plus, etc. So that is equal to 1, which is just tan of pi on 4, plus a half tan of pi on 8, plus 1/4 tan of pi on 2 times 8 is 16, plus dot, 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 dot. So that's if we let x equal pi on 2. We have this series, which is the summation of this. Now we know that that is equal to 2 over x minus 2 cot x, which is 2 divided by pi over 2 minus 2 times cot of pi on 2, which is equal to 2 divided by pi on 2 is 2 times 2 on pi, which is 4 on pi, minus, now, cot of pi on 2. So again, 4 on pi minus 2 times, now the cot of pi on 2 is 0, so it's 4 on pi. And so therefore, this expression is equal to 4 on pi. So therefore, tan of pi on 4 plus a half tan pi on 8 plus 1/4 tan pi on 16 plus is equal to 4 over pi. Okay, and that's the end of that question. This is 2012 HSC question 16b, this induction question here. So first part, show that the inverse tan of x plus inverse tan of y equals inverse tan of x plus y over 1 minus x times y for x less than 1, absolute value, sorry, of x less than 1, and absolute value of y less than 1. If we let a equal inverse tan of x, therefore x equals tan of a, and if we let b equal inverse tan of y, then y equals tan of b. Now we know that the tan of a plus b equals tan of a plus tan of b minus, over 1 minus tan of a times tan of b. So therefore that's equal to x plus y over 1 minus xy. That's what tan of a plus b is. So therefore a plus b is the inverse tan of x plus y over 1 minus xy, or inverse tan of x plus inverse tan of y equals inverse tan of x plus y over 1 minus xy as required. Now for part 2, use mathematical induction to prove that the sum from j equals 1 to n of inverse tan of 1 over 2j squared equals the inverse tan of n over n plus 1. Okay, prove true. So part 1, prove true for n equals 1. So the left hand side equals the inverse tan of 1 over 2 times 1 squared, which is the inverse tan of a half. And the right hand side is equal to the inverse tan of 1 over 1 plus 1, which is equal to inverse tan of a half as well. So therefore true for n equals 1. Now we're going to assume true for n equals k. That is, we're going to assume that the sum from j to 1 through to k of inverse tan of 1 over 2j squared is equal to the inverse tan of k over k plus 1. And step 3, prove true for n equals k plus 1. That is, we need to prove that the sum from j equals 1 to k plus 1 of inverse tan of 1 over 2j squared equals the inverse tan of k plus 1 over k plus 1 plus 1, which is k plus 2. So left hand side is equal to sum from j is 1 to k plus 1 of inverse tan of 1 over 2j squared, which is the sum from j is 1 to k of the inverse tan of 1 over 2j squared plus the k plus 1th term, which is the inverse tan of 1 over 2 times k plus 1 squared. Now, using the assumption from part 2, we can replace sum from j is 1 to k of inverse tan of 1 over 2j squared with inverse tan of k over k plus 1 plus the inverse tan of 1 over 2 bracket k plus 1 squared. Now this is in the form of inverse tan of x plus inverse tan of y. So we're going to use this result here from B part 1, that the inverse tan of x plus inverse tan of y is inverse tan of x plus y over 1 minus x times y. So therefore that is equal to the inverse tan of x plus y will be k over k plus 1 plus 1 over 2 bracket k plus 1 squared. And all of that is divided by 1 minus x, which is k plus 1, times 1 over 2 bracket k plus 1 squared. Now if we multiply the numerator and denominator, so multiply through the numerator and denominator by 2 bracket k plus 1 squared, we will get the inverse tan of we'll get 2k times k plus 1 squared. One of the squares cancels with this, plus 1. Actually, we're not multiplying by 2 bracket k plus 1 squared. We're multiplying by 2 bracket k plus 1 cubed, because we've got k plus 1 times k plus 1 squared, so sorry about that. So we're multiplying through by 2 bracket k plus 1 cubed. So we will get 2k k plus 1 squared plus, we'll get another k plus 1 here over, so multiply through the numerator and denominator by 2 bracket k plus 1 cubed. Over 2 bracket k plus 1 cubed minus, we'll get 2k k plus 1 squared. Oh no, we won't. Sorry, this is all one term, remember? So we've got 2k plus 1 cubed here, so we'll just get minus k. Okay, so just be careful there. Okay, we're trying to show that this is equal to inverse tan of k plus 1 over k plus 2. So we want sort of a k plus 1 here on the numerator factored out and a k plus 2 somehow on the denominator. So this is inverse tan. So we can see we've got a common factor of k plus 1 on the numerator. And what's left over will be 2k bracket k plus 1 plus 1. And on the denominator, the only thing we can really do here at the moment is to expand. So we've got we've got k cubed plus 3k squared plus 3k plus 1, expanding that, minus k, which is inverse tan of k plus 1 on the numerator times 2k squared plus 2k plus 1. So we've got 2k squared plus 2k plus 1 over, now on the denominator we've got 2k cubed plus 6k squared, we've got plus 6k, we've got minus k, which is plus 5k, and we've got plus 2 here. Now, what we need is k plus 1 on k plus 2. So what we're hoping here for is inverse tan of k plus 1 over 2k squared plus 2k plus 1. We need, let's hope that if k plus 2 is a factor of this, and we'll be able to tell if we substitute, so we want k plus 2 really to be a factor of this. Okay, so if k plus 2 is a factor, then if we substitute negative 2 for k, we should get 0 here. So 2 times negative 8 is negative 16, plus 6 times 4 is 24. Then we've got minus 10 plus 2, and that gives us 0. So we know that k plus 2 is a factor. Okay, and what I'm going to do here, I'm just going to put 2k squared plus 2k plus 1, because we know to get 2k cubed, so we can just do this by inspection as well. 2k squared times k is 2k cubed. If we look at the constants, 2 times 1 is 2. And how do we get the 6k squared? The 6k squared would be formed from 2 times 2k squared is 4k squared, and 2k times k gives me 6k squared, and the k term will come from 2k times 2, which is 4k, and it'll also come from 1 times k, which is 5k. So therefore this factorization is correct, and cancelling those common factors, we get inverse tan of k plus 1 over k plus 2, which equals the right hand side. So therefore it is true for n greater than or equal to 1 by mathematical induction. Question is to find the limit as n approaches infinity from j equals 1 to n of inverse tan of 1 over 2j squared. Now we know from from our result proven in part 2 that therefore we can say that the limit as n approaches infinity from j is 1, inverse tan of 1 over 2j squared will be equal to the limit as n approaches infinity of inverse tan of n over n plus 1. Now, as n approaches infinity, so as n approaches infinity, you will get this thing here approaching 1. So therefore that's inverse tan of 1, which is equal to pi on 4. Okay, so therefore that's our solution there for limit as n approaches infinity of this. And that's the end of that question as well.